Welcome to the Hypnos Sleep Channel. Tonight, Hypnos, the ancient Greek god of sleep, will guide us gently through a quiet fleet of impossible vessels. Living ships, planet-killing stations, wandering probes, city-sized shadows, and moon-sized machines from science fiction. We will let each fictional spacecraft appear for a moment on the view screen, not as a challenge to believe it, but as a doorway into what the real universe asks of any object that tries to cross deep space. For now, imagine a silent observation deck high above Earth. Below you, the night side of the planet turns slowly, its cities glowing like small constellations on land. Above you, the real stars are scattered across the dark, separated by distances so large that even light needs years to make the journey. Between Earth and those stars, the imagination has built many ships. Some are sleek and familiar. Some are strange enough to look grown instead of manufactured. Some are so large that the word spaceship begins to blur into city, asteroid, moon, or moving world. In fiction, enormous ships can glide through space with calm certainty. They can arrive over planets, open hangars, bend light, cross galaxies, or drill into worlds. In reality, size changes everything. A small spacecraft must solve propulsion, heat, power, radiation, guidance, and communication. A gigantic spacecraft must solve all of those problems again, but with mass and structure multiplied until the ship becomes a world-sized engineering question. The larger the vessel becomes, the more it has to behave like a bridge, a power plant, a habitat, a mountain, and sometimes a small planet all at once. So tonight, we will not simply count ships. We will let the source list become a calm tour through scale. We will move from a living bioship only a few miles long to star dreadnoughts and city destroyers, to probes wrapped in mystery, to battle stations and motherships large enough to make human spacecraft feel like dust in a beam of sunlight. At each stop, the crew will ask the same quiet question. If this ship were waiting in real space, what would physics notice first? The first shape in the dark is the Lex, the strange living bioship from the series that bears its name. In the story, the Lex is not simply a metal vessel with engines bolted to its stern. It is grown, hungry, insect-like, and immense, often described as roughly 10 kilometers long. From a distance, it can resemble a wingless dragonfly drifting through a black ocean, a biological weapon with cavernous interiors and a crew so small that the ship itself feels more like a wandering creature than a machine. On the bridge of a more ordinary starship, the first sensor officer would not call the Lex beautiful or ugly. The first report would be about structure. 10 kilometers is longer than many cities are wide. On Earth, a bridge only a few kilometers long already needs careful engineering to hold its own weight against gravity, wind, heat expansion, vibration, and the slow fatigue of materials. In space, a ship does not need to stand on the ground, which helps. But it still needs to survive acceleration, rotation, thermal stress, docking forces, impacts, and the push of its own engines. A living ship makes the question even stranger. Real organisms are excellent at growth, repair, sensing, and self-regulation. Bones are light and strong for their mass. Shells and exoskeletons can distribute loads. Tree trunks can move water upward against gravity and survive storms for centuries. But living tissue is also full of water, chemistry, temperature limits, and maintenance needs. A 10-kilometer organism in vacuum would need protection from radiation, pressure loss, freezing, boiling, and micrometeorites. It would need a way to move heat around its body because space is not cold in the simple way a room is cold. In space, heat leaves mainly by radiation, slowly from surfaces facing the dark. If the Lex were real, a science officer might not begin with weapons. She might ask how blood, coolant, or some unknown internal fluid could circulate across miles of living chambers. She might ask whether the ship had organs like reactors, nerves like optical cables, and bones like carbon composite trusses. She might ask how a wound in one part of the hull could seal before pressure escaped through kilometers of passageway. The fiction gives us a giant insect ship. The reality gives us a lesson in scale. Once biology becomes architecture, every heartbeat has to become infrastructure. This is why the Lex is a useful first doorway. It lets us picture a ship as an ecosystem. Real long-duration spacecraft may one day need to be partly ecological, even if they are never alive in the Lex sense. Crews traveling for years would need closed-loop air, water recycling, food production, waste processing, microbial balance, radiation shelter, and repair systems that do not depend on constant resupply from Earth. A starship is not just a vehicle. At interplanetary or interstellar durations, it becomes a traveling environment. From Earth orbit, even the International Space Station depends on regular cargo visits. From Mars, supplies would take months to arrive. From the outer planets, a message itself can take hours to cross the solar system. From Proxima Centauri, the nearest star system beyond the Sun, light takes a little more than 4 years to reach us. Any ship that travels beyond the easy reach of home must become less like an aircraft and more like a small, patient world. The Lex turns that idea into a strange fantasy creature. Real engineering turns it into a list of quieter questions. What can be repaired? What can be grown? What can be recycled? What can fail gracefully? And how much living complexity a vessel can carry without becoming harder to protect than a simple machine. The next silhouette is sharper. It is the Executor-class star dreadnought, the long dark blade from Star Wars, often called a superstar destroyer. In fictional terms, the Executor is a command ship, a symbol of imperial scale and intimidation. In common technical references, it is about 19 kilometers long, almost twice the length often given for the Lex, and shaped less like an animal than a dagger laid across the stars. On the view screen, such a vessel would not simply be large. It would be long enough that one end of the hull could be in a slightly different orbital environment from the other. If it were near a planet, the bow and stern would feel tiny differences in gravity. If it accelerated hard, the entire structure would have to carry the force from its engines forward through its spine. A real spacecraft this long could not be treated as one solid object in the casual way a film camera treats it. It would flex, it would vibrate, it would have normal modes, stress points, expansion joints, and thermal gradients. Imagine an engineer standing in a maintenance gallery somewhere inside the Executor. The engines ignite far behind her. The thrust does not arrive everywhere at once like a magic command. It travels through structure as stress, through metal or composite as waves, through supports and decks and frames. If the acceleration is gentle, the vessel can remain calm. If the acceleration is extreme, the ship is trying to tear itself into 1,000 arguments about inertia. This is one of the great quiet boundaries between cinematic ships and real ones. Fiction often shows enormous vessels turning like boats, but in space, turning is not free. A 19-kilometer vessel has enormous rotational inertia. To change its orientation, it needs torque, reaction control, gyroscopes, thrust vectoring, or some fictional equivalent. The longer the ship, the more careful the maneuver. A fast turn at the bow is not the same as a fast turn at the center. The crew would feel the motion differently depending on where they stood. Real spacecraft are usually compact because compact structures are easier to control. The Apollo command module was not shaped like a grand ocean liner. Modern probes fold their solar arrays and instruments carefully because every meter matters. The James Webb Space Telescope had to unfold in a choreography of membranes, mirrors, latches, and tension. Even a telescope only the size of a tennis court became one of the most delicate deployments ever attempted. A star dreadnought stretches that difficulty into the realm of cities. And then there is crew. Fictional megaships can hold thousands or hundreds of thousands of beings. Reality would ask about air volume, food, water, heat, waste, medical care, social structure, fire safety, radiation storms, and the simple problem of moving from one end to the other. At ordinary walking speed, crossing 19 kilometers is not a quick errand. If a ship that large suffered a failure near the stern, the response would need internal transit systems, compartments, remote robotics, and a command architecture more like a city emergency network than a bridge crew shouting orders. The executor therefore becomes a doorway into the physics of command at scale. A small spacecraft can be intimate. A giant warship is a civilization of systems. It needs hierarchy, redundancy, sensors, automatic isolation, and local control. Real spacecraft already use autonomy because radio delay and complexity make constant hand control impossible. A vessel many kilometers long would need nervous systems of its own, not because it is alive like the Lex, but because no bridge crew could personally manage every valve, circuit, temperature gradient, and structural alarm in real time. And past the executor, the tour carries us toward Earth. A shadow spreads across cloud tops and coastlines. This is the city destroyer from Independence Day, a saucer-like alien vessel often described as about 15 miles, or roughly 25 kilometers, across. In the film, it parks above a human city like a lid over daylight. The image is simple and powerful, a machine large enough to turn a city into a target beneath its center. The real science doorway here is not faster than light travel. It is atmosphere. A vessel 25 kilometers across entering or hovering in a planet's atmosphere would not be a quiet object. It would interact with air on a scale comparable to weather. Air has mass. Pushing a vast hull through it would compress, heat, displace, and disturb the atmosphere. If the ship hovered without visible support, something would have to counter gravity, and whatever did that would transfer forces into the air, the ground, or a field we do not know how to create. From a rooftop below, the first real effect might not be the weapon. It might be wind. A city-sized craft moving overhead would shove air aside. If it descended slowly, pressure patterns could change. If it held position by blasting engines downward, the ground would be scoured. If it used some fictional anti-gravity field, the field would have to interact with mass in a way real physics has never demonstrated for machines. We know how to use thrust. We know how to use lift in atmosphere. We know orbital motion can keep an object falling around Earth. We do not know how to make a huge object simply ignore weight. This is where a calm fiction to reality pivot matters. In real life, hovering is expensive. A helicopter hovers by pushing air down. A rocket hovers by throwing hot exhaust down at high speed. A balloon hovers by displacing heavier air. A spacecraft in orbit does not hover above one city. It moves around Earth at orbital speed. To remain fixed above one point without orbiting, especially at low altitude, would require continuous support. A city destroyer makes that support invisible, which is fine for story, but the hidden physics bill is enormous. The city destroyer also invites a question about surfaces. A 25-kilometer hull has a huge cross-section. In space, dust grains and micrometeorites strike at high speeds. In atmosphere, clouds, ice, lightning, turbulence, and weather become engineering realities. On Earth, a large aircraft already worries about lightning, icing, fatigue, and pressure cycles. A city-sized ship moving between space and atmosphere would need skin that behaves like spacecraft heat shield, aircraft surface, armor, and structural shell all at once. If a probe flew beneath such a vessel and looked upward, it would see not just a ceiling, but a landscape. Ridges, weapon apertures, bays, shadowed recesses, and lights would pass overhead like terrain. That image is wonderful for fiction. In reality, it reminds us that any very large spacecraft would become geography. Once a ship is wide enough, weather, maintenance, navigation, and damage are local. The underside is not one part, it is districts. From there, the tour moves into Babylon 5 and the Vorlon planet Killer. The source transcript gives a much smaller number in one place, but better-known technical references describe the Vorlon planet Killer as tens of kilometers long, perhaps in the range of 40 or 50 kilometers, with uncertainty. In fiction, it is not simply a ship. It is an ancient, almost incomprehensible weapon, a vessel built by a civilization far older than humanity, able to threaten entire worlds. The real science doorway is energy. Destroying a planet is not like breaking a stone. A planet is held together by gravity. Earth is not a loose ball of dirt. It is a massive, self-gravitating body compressed by its own weight, differentiated into core, mantle, crust, oceans, and atmosphere. To truly blow a planet apart, a machine would need to supply energy on a scale far beyond human weapons. Even disrupting the surface completely is already beyond ordinary imagination. Unbinding a planet gravitationally is another step again. On a Starship bridge, the captain might ask whether the planet killer is charging its main weapon. A real physicist would ask where the waste heat goes. Any weapon that releases tremendous energy also has to manage energy before release. Power generation, storage, focusing, cooling, and structural recoil become part of the same problem. If the beam is electromagnetic radiation, charged particles, plasma, gravity manipulation, or some exotic fictional effect, each version carries different physics. But all of them face a boundary. Energy cannot simply appear, and heat cannot simply vanish. Heat is one of the quiet rulers of spaceflight. In atmosphere, air can carry heat away. In space, a spacecraft must radiate heat into darkness. Radiators, reflective surfaces, fluid loops, phase change materials, and careful power cycles matter. A planet-killing weapon would be less like a cannon and more like a Starship-sized power industry. The ship would need generators or stored energy so great that even a tiny inefficiency could become a disaster for the vessel itself. This is why real spacecraft often look delicate. Solar panels, antennas, radiators, insulation blankets, and instrument booms are not decorations. They are survival systems. A ship that handles enormous power would need vast thermal management unless its fictional technology bypasses the ordinary rules. The Vorlon planet killer, with its organic and ancient design language, suggests technology so advanced it looks biological. Reality would still ask the same quiet question: where does the heat go? The planet killer also turns us toward moral scale, gently, without needing alarm. Science fiction often uses giant ships to make power visible. Real science teaches that the more powerful a technology becomes, the more carefully it must be understood. Rockets, nuclear reactors, particle accelerators, and planetary defense systems are all examples of energy guided by knowledge and constraint. The peaceful lesson hidden inside a fictional weapon is that mastery of physics is never only about force. It is about control, stability, prediction, and responsibility. Next comes one of the most mysterious vessels in Star Trek, the whale probe from the voyage home. In the story, a huge cylindrical probe approaches Earth, disables power systems, disrupts the planet, and seems to be calling for humpback whales. It is not a warship in the familiar sense. It is a message from somewhere else, but a message so powerful and so indifferent to human systems that Earth becomes fragile beneath it. The whale probe is a doorway into communication. Not every alien vessel in fiction has to arrive with conquest. Some arrive with questions. The real universe already sends messages, though not intentional ones in the human sense. Pulsars flash with astonishing regularity. Stars reveal their chemical fingerprints through spectra. Exoplanets tug on their stars or dim them during transits. Gravitational waves ripple through space-time from merging black holes and neutron stars. The cosmos is full of signals, but most are not addressed to us. They are physical processes, waiting to be interpreted. If a real probe came from another civilization, communication would be the deepest problem. It would not be enough to transmit loudly. The sender and receiver would need shared assumptions, frequency, timing, symbols, mathematics, reference frames, and intent. Even on Earth, whales and humans share a planet and still do not fully share a language. Whale songs travel through water across long distances. They carry structure and change through time. But understanding another intelligence requires more than detecting sound. It requires context. The Star Trek image is moving because the probe is not looking for humanity. It is looking for another voice from Earth. In real science, this helps us remember that intelligence may not always look toward us first. If life exists elsewhere, it may communicate through chemistry, pressure waves, electromagnetic pulses, light flashes, magnetic fields, or something we have not learned to notice. Human radio is only one possible doorway. The whale probe also raises the issue of environmental coupling. In the film, its signal affects Earth dramatically. In reality, a powerful signal passing through atmosphere or ocean would interact with matter depending on its wavelength and energy. Radio waves, microwaves, visible light, ultraviolet, X-rays, particles, and gravity waves all behave differently. Some pass through air easily. Some are absorbed. Some ionize atoms. Some heat matter. A probe strong enough to disturb a planet would not merely be communicating. It would be depositing energy into an environment. Imagine standing not on Earth but on a small research vessel near Jupiter, listening for the probe from far away. Jupiter's magnetosphere is already a giant natural radio source. Its moons move through plasma. Charged particles spiral along magnetic fields. The solar wind presses against planetary shields. A real alien signal would have to be distinguished from all this natural noise. The crew would not simply hear a message. They would find a pattern hidden in a storm of physics. The whale probe is therefore one of the gentlest strange ships on the list. It reminds us that a large vessel does not have to be measured only by weapons or engines. It can be measured by the difficulty of being understood. Then the tour reaches Vigor, the vast entity from Star Trek: The Motion Picture. Vigor is one of the great scale puzzles of science fiction. Depending on the version and interpretation, the surrounding energy cloud is described as either a few astronomical units across or far larger, with the original theatrical dialogue giving a famously enormous number. An astronomical unit is roughly the average distance from Earth to the Sun. Light takes about 8 minutes to cross that distance. So even the smaller version of V-Gear's cloud is not merely ship-sized. It is solar system-sized in feeling. On the bridge, this would change everything. A normal ship can be approached from outside. V-Gear is more like entering a weather system, a nebula, or a miniature cosmic environment. The Enterprise does not simply dock. It passes into layers of cloud and energy toward a hidden center. The fiction turns a spacecraft into an interior cosmos. Real space gives us many objects that are known by their envelopes before their cores. A comet may appear as a glowing coma and tail, far larger than its icy nucleus. A star is known by its photosphere and atmosphere, not by touching its core. A nebula can spread across light years while being more rarefied than any vacuum we can make on Earth. A black hole may be inferred from accretion light, stellar orbits, gravitational waves, and lensing, while the event horizon itself remains a boundary beyond which information cannot return. V-Gear belongs to that family of images. The visible form is not the whole object. The real science doorway is measurement. How do you measure something too large to grasp in one view? Astronomers use parallax, redshift, standard candles, orbital motion, radar ranging, light curves, spectra, gravitational effects, and timing. A Starship crew inside V-Gear would do something similar at a smaller scale. They would map gradients, they would compare signal delay, they would measure particles, fields, radiation, temperature, composition, and motion. They would build a map from partial evidence. The size controversy around V-Gear is useful rather than embarrassing. It shows how scale in fiction can exceed the story's own practical needs. A cloud tens of astronomical units wide would engulf enormous regions of the solar system. Even a 2 astronomical unit cloud would span the diameter of Earth's orbit. If such a structure entered the inner solar system as ordinary matter, gravity, radiation, and drag interactions would be profound. So, the calm scientific boundary is simple. V-Gear is not a plausible conventional solid vessel. It is a fictional entity wrapped in effects that behave more like controlled energy, field structure, or symbolic cosmic presence than ordinary matter. And yet, the idea still opens real wonder. Humanity has already sent small probes outward. Voyager 1 and Voyager 2 have crossed into interstellar space, carrying instruments, records, and the long memory of their makers. They are not V-Gear, they are fragile, silent compared with stars, and limited by tiny power sources. But they are real messengers from Earth. They remind us that a probe can become more meaningful with distance. The farther it travels, the more it becomes a question sent into time. V-Gear asks what would happen if a machine learned, returned, and wanted to know its creator. Real science cannot confirm such a path, but real science does know that information can outlive the moment that made it. Light from Andromeda left that galaxy around 2.5 million years ago before reaching our eyes. Meteorites preserve chemistry older than Earth. Space probes carry human design beyond the planets. The universe is full of messages delayed by distance. After V-Gear, we come to the Voth Fortress ship from Star Trek Online, commonly listed at about 134 kilometers long. This is game continuity rather than a television spacecraft in the usual sense, but it is an excellent doorway into ships that become mobile cities. A vessel more than 100 kilometers long is no longer just large. It is comparable in length to a region on a map. It could contain hangars, factories, habitats, transit systems, storage, reactors, farms, and internal landscapes. At that scale, the word fortress matters. A fortress is not only a wall, it is a defended place. A mobile fortress would need layers, outer shell, inner compartments, redundant command centers, power grids, life support zones, repair docks, and protected cores. If a small ship is a tool, a fortress ship is infrastructure under motion. The real science doorway is habitat design. We do not yet have city ships, but we have studied space settlements for decades. A large, rotating habitat could create artificial gravity through spin. The physics is simple in principle. Inside a rotating cylinder or ring, the floor pushes inward on your feet, and your body experiences that support as a gravity-like sensation. But the engineering is not simple. The structure must be large enough that rotation does not create uncomfortable differences between head and feet. It must handle stress around the rim. It must manage atmosphere, lighting, agriculture, water, waste, and thermal balance. A 100-kilometer vessel could, in fiction, contain rotating drums, stacked decks, or artificial gravity fields. In real engineering, artificial gravity by rotation is the nearest known path. But rotation changes the layout. Docking becomes tricky. Bearings, seals, moving fluids, and emergency response all become design problems. A ship shaped like a fortress might choose partial gravity in certain habitats, microgravity in industrial zones, and shielded storm shelters near the core. Radiation is another quiet ruler. On Earth, the atmosphere and magnetic field protect life from much of space weather and cosmic radiation. In deep space, a city ship would need shielding. Water is good shielding. Soil can help. Fuel, waste tanks, and storage can be arranged around living quarters. A ship large enough to carry its own lakes, ice reservoirs, or thick, regolith-like walls could protect a population better than a thin metal hull. But every kilogram of shielding must be moved. This is the constant exchange in real spacecraft design. Protection adds mass. Mass demands propulsion. Propulsion demands energy. Energy creates heat. Heat demands radiators, and radiators add area and vulnerability. A gigantic fortress ship does not escape this chain. It only moves the chain onto a grander scale. From a front row viewpoint, imagine a runabout approaching such a vessel. At first, the ship is a line against stars. Then it becomes a wall. Then the wall becomes a horizon. Docking lights appear not as lamps but as constellations arranged by engineers. The traffic pattern around the hull resembles an airport, a harbor, and an orbital station together. Real physics would make every approach slow and careful because relative velocity is everything. A tiny mistake near a 100-kilometer structure can become a high-speed impact. The Voth fortress ship reminds us that the dream of a huge starship is also the dream of taking a city away from a planet. Real life has not done this. But every space station, habitat study, lunar base plan, Mars transit design, and closed ecosystem experiment touches one piece of that dream. The next object is famous enough that the source transcript almost gets quiet around it, the Death Star. Strictly speaking, the Death Star is a battle station more than a spaceship, but it moves through space, crosses interstellar distances in the fiction, and carries the most recognizable lesson in fictional megastructure scale. It is not shaped like a ship. It is shaped like a small moon, because the story wants characters to mistake it for one. The real science doorway is gravity. Any object large enough and massive enough begins to act less like a vehicle and more like a celestial body. The Death Star is often given a diameter on the order of 100+ kilometers, depending on source and version. That is asteroid scale. not planet scale. If it were made mostly of metal and machinery rather than low-density rock and voids, its mass could be enormous. It might have noticeable gravity at its surface, though not Earth-like unless it were far more massive or built with extraordinary density. The exact value would depend on composition, hollowness, and mass distribution. This matters because giant fictional stations often ignore their own gravity. A real object the size of a small moon would attract dust, debris, spacecraft, and people. It would have an escape velocity. It would perturb nearby orbits. It would need station keeping if placed near a planet. If it carried artificial gravity inside, that artificial gravity would interact conceptually with the natural gravity from its mass, unless the story handwaves both away. The Death Star also opens the question of building in space. On Earth, a structure 100 kilometers wide would be crushed by its own weight unless it were supported by the ground and designed around gravity. In space, large structures can be assembled without resting on a foundation, but they still face stress from rotation, acceleration, internal pressure, docking, impacts, and thermal cycling. If one side faces a star and the other faces deep space, temperatures can differ dramatically. Materials expand and contract. Joints must survive. Seals must remain tight. A spherical station has advantages. Pressure vessels like spheres because a sphere distributes internal pressure evenly. Fuel tanks and crew modules often use rounded forms for related reasons. But a Death Star is not just a pressure vessel. It is a hollowed, layered, inhabited, weaponized world. The more tunnels, shafts, hangars, reactors, and cavities it contains, the more its structure becomes a three-dimensional puzzle. There is also the matter of the famous weakness. Fiction needs a path for courage. Reality would phrase the issue differently. Complex systems fail through coupling. A small vulnerability becomes catastrophic when it connects directly to the core function of a system without isolation, redundancy, or fail-safes. In real engineering, spacecraft are designed with fault tolerance because space is unforgiving. Valves can stick, sensors can fail, software can misread a condition. A safe design assumes failures will happen and tries to keep them local. So the Death Star, viewed gently, becomes a lesson in systems engineering. The larger and more powerful the machine, the more important it is to prevent one local event from reaching the heart. A starship, a city, a power grid, and a spacecraft all share this principle. Isolation is kindness in design. Redundancy is patience. A good system does not assume perfection. It assumes the universe will eventually test every joint. Then, beyond the Death Star, comes the alien mothership from Independence Day, the great carrier that dispatches city destroyers. In the first film's imagery, the mothership feels less like a single spacecraft and more like a mobile invasion ecology. It carries smaller vessels, coordinates them, and hangs near Earth as a central nervous system for the fleet. The real science doorway is logistics. A carrier is not just bigger because it wants to look impressive. A carrier exists to move other vehicles, fuel them, repair them, coordinate them, and support the beings or machines that operate them. On Earth, an aircraft carrier is a floating airport, city, power plant, warehouse, command center, and defensive platform. In space, the same idea expands. A mothership must manage propellant, spare parts, heat, communications, navigation, and traffic. If a mothership carried dozens of city-sized vessels, its internal volume would have to be staggering. Hangars would be landscapes. Docking would require careful relative motion. A smaller ship leaving a giant bay would need to avoid exhaust, debris, collision paths, and gravitational or field effects. The command problem alone would be immense. Even light-speed communication inside a very large structure has delay if the distances grow enough. Across 1,000 kilometers, light takes only a few thousandths of a second, but high-speed automated systems can still care about such delays. Across astronomical distances, delay becomes central. For real human spacecraft, logistics is already one of the hardest parts. A Mars mission is not difficult only because Mars is far away. It is difficult because everything needed for the crew must either be carried, made, recycled, or found there. Fuel, oxygen, water, food, spare parts, medical supplies, radiation shielding, and return capability all matter. The farther from Earth a mission goes, the less Earth can behave like a nearby warehouse. A mothership solves this in fiction by being enormous. Reality would ask how it got enormous. Did it form in orbit around its homeworld? Was it built from asteroids? Did it mine moons? Did it assemble itself over centuries? Large spacecraft are easier to imagine if they are built in space rather than launched from a planet. Launching mass from a deep gravity well is expensive. Earth is generous to life, but demanding to rockets. Every kilogram lifted to orbit requires energy, staging, and engineering. This is why many real future space concepts begin with in-space resources. The Moon has lower gravity than Earth. Asteroids contain metals and volatiles. Mars has carbon dioxide atmosphere and water ice in some regions. If humanity ever builds truly huge structures beyond Earth, the materials may come from places where gravity is easier to escape. A fictional alien mothership hints at a civilization that has already crossed that threshold, not merely traveling through space, but using space as its construction yard. The final and largest image from the source is the Harvester Queen mothership from Independence Day, Resurgence, often described in the fiction as roughly 3,000 miles across, comparable to a major fraction of Earth's diameter. At that point, the word ship becomes almost poetic. A 3,000-mile vessel is not merely city-sized, station-sized, or asteroid-sized. It is planetary in presence. If such an object came near Earth in reality, the first question would be gravity. Something thousands of miles across, if made of ordinary dense matter, would have enormous mass. Its gravitational pull could affect tides, satellites, oceans, the Moon's orbit, and the stability of near-Earth space. If it somehow had very low density, more like a vast hollow shell or engineered lattice, gravity might be less than its size suggests. But then structure becomes astonishingly difficult. A planet-sized shell must resist stresses across continental distances. The film imagines a vessel that can land across part of Earth and drill toward the core. The real science boundary is clear. Penetrating a planet's crust, mantle, and core is not like lowering a straw into a drink. Earth's interior is hot, pressurized, layered, and dynamic. The deepest human-made boreholes only reach a tiny fraction of the way through the crust. The mantle flows over geological time. The outer core is liquid metal. The inner core is solid under immense pressure. A machine interacting with the core would be dealing with heat, pressure, chemistry, seismic energy, and planetary rotation on scales beyond any known engineering. But there is a quieter real idea inside the fantasy. Planets are not solid marbles. They are active worlds with internal energy. Earth has heat left from formation, heat from radioactive decay, and heat moved by convection. That internal heat helps drive plate tectonics, volcanism, mountain building, and the recycling of carbon over deep time. Earth's magnetic field is linked to motion in the metallic outer core, and that magnetic field helps shield the planet from the solar wind. The inside of a planet matters profoundly to the life on its surface. So when fiction imagines a mothership harvesting a planet's core, real science can answer with planetary anatomy. From the surface, Earth feels calm. From orbit, it looks blue and white. But beneath the crust is a long story of heat, pressure, minerals, metal, and time. A starship does not need to drill into that story for it to be astonishing. The real planet beneath our feet is already more complex than a simple target. The Harvester mothership also helps us think about megastructure limits. A vessel thousands of miles across would have to manage internal gravity, structural loads, communication delays, local weather if it contains atmosphere, power distribution across continental distances, and protection from impacts. Even if built in microgravity, such a structure would behave less like a ship and more like an artificial world. Different regions could have different climates, pressures, repair systems, and local emergencies. Command from a single bridge would be a fiction of convenience. The real vessel would need distributed intelligence. In that sense, the largest fictional ships point back to planets. Earth is the only world-sized life support system we know works for humans without spacesuits. It has atmosphere, oceans, soil, magnetic shielding, sunlight, recycling chemistry, and a biosphere that has been tuning itself for billions of years. Every starship is, in some way, a small attempt to imitate what Earth already does naturally. Now the observation deck grows quiet again, and the fleet we have passed begins to arrange itself in memory. The Lex taught us that a ship can be imagined as a living ecosystem. The Executor taught us that length brings inertia, stress, and command complexity. The City Destroyer taught us that atmosphere is not empty space, and hovering over a world is a physics problem. The Vorlon Planet Killer taught us that energy and heat are inseparable from power. The Whale Probe taught us that communication with another intelligence may be stranger than combat. Vigir taught us that some vessels are measured first by their envelopes, signals, and mysteries. The Voth Fortress ship taught us that a mobile city must solve habitat, radiation, and transit. The Death Star taught us that giant structures become systems of gravity, failure, and redundancy. The Alien Mothership taught us that carriers are logistics made visible. And the Harvester Queen Mothership taught us that beyond a certain size, a ship becomes an artificial world. From the bridge, the crew does not need to choose which fictional vessel is the strongest. That is the old debate. The calmer question is more interesting. Which one opens the widest door into reality? The answer may change depending on what we want to learn. For biology, the Lex. For structures, the Executor. For atmosphere, the City Destroyer. For energy, the Planet Killer. For language, the Whale Probe. For measurement, Vigir. For habitats, the Voth Fortress. For systems engineering, the Death Star. For logistics, the Mothership. For planetary science, the Harvester. And beyond all of them is the real night sky. No fictional ship, however vast, is larger than the distances between stars. A 19-kilometer dreadnought is enormous beside a human city, but light crosses 19 kilometers in a tiny fraction of a second. Light from the sun takes about 8 minutes to reach Earth. Light from Neptune takes hours to reach us. Light from the nearest star takes years. Light from Andromeda takes millions of years. The universe is so wide that even our grandest imaginary ships become small again when placed between galaxies. That smallness is not a disappointment. It is the source of the wonder. Science fiction gives us vessels big enough to see our questions. Real science gives those questions depth. How do we move mass? How do we protect life? How do we shed heat? How do we cross distance? How do we communicate? How do we build without a planet under our feet? How do we remember that every machine, no matter how powerful, must still answer to the quiet rules of the universe? The fictional fleet drifts farther from the observation deck now. The dagger ships, saucers, cylinders, bioships, stations, and motherships become silhouettes against the Milky Way. Earth turns below, still the most generous vessel we know, carrying oceans, forests, cities, clouds, and sleeping rooms through space at orbital speed around the sun. For now, the bridge lights dim, the sensor logs close. The great ships remain outside the window, impossible and beautiful, each one less a prediction than a question, and the real stars continue beyond them, patient, distant, and bright enough to guide every story home.